Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Now that we've got a good understanding of how to work with limits in an algebraic setting, we can proceed to look at more theory-based ideas instead of computational problems. We'll warm up with a limit exercise, and then move on to an important limit theorem that you'll likely get exposure to in your first calculus course. But before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first exercise, we want to simplify this limit here. So we're given that our function f of x is equal to x squared. Now to do this, we're just going to substitute it in. So this is going to be the limit as h approaches 0 of, our numerator is f of x plus h minus f of x. So if f of x is x squared, then f of x plus h is going to be x plus h all squared. And then we're subtracting f of x, which is x squared, and this is all over h. And now we're just going to do a little bit of expansion. So this is equal to the limit as h approaches 0, and then we're going to expand our x plus h squared. So that's going to be x squared plus 2xh plus h squared. And then we copy down the rest, which is minus x squared over h. Now notice how we have an x squared minus an x squared. So then they get canceled out, which means we're left with limit as h approaches 0 of, our numerator is now going to be 2xh plus h squared. So now notice how we have an h in both terms. That means we can go ahead and factor it out. So we get limit as h approaches 0. We have h times 2x plus h. And this is exactly what we want to see because currently we can't use our direct substitution rule because of the h in our denominator. But now that we have an h on top, we can now cancel out the h in the numerator and the denominator. So this means our limit is now going to be limit as h approaches 0 of 2x plus h. And now, because 0 is within the domain of this expression here, we can use our direct substitution rule, and that's going to give us this is equal to 2x. And just a quick note on notation, notice how we need to keep writing our limit until we can actually apply our direct substitution rule or evaluate the limit somehow. So make sure you always write your limit until the step where you actually apply it. And now we're going to move on to the main topic of this video, which is the squeeze theorem. The squeeze theorem says that if our function g of x is in between two functions, which we will call f of x and h of x, when x is near a, except possibly at a. And the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a, and they're both equal to L, then we're going to have the limit of our function g of x as x approaches a is also equal to L. So we're going to demonstrate what that looks like with a diagram. So let's say we have our x and y axes here. Now we only care about the behavior as x approaches a. So let's say that a is right over here. Now we're going to have some random function f of x. So let's say it looks something like this. So this is our f of x. And then we're going to have another function h of x. And the only thing is that we know that the limit of both f of x and h of x as x approaches a is equal to L. So let's go ahead and write that down first. So here is a, and the limit of f of x as x approaches a is going to be equal to L. So that's right over here. This is going to be our L. And now we know that h of x has that exact same limit at a. So we're going to go and draw the curve h of x, and we don't care what it looks like anywhere else. The only thing is that it has to be right over here at x is equal to a. So let's say it looks something like this. And it just has to be at that point. And then let's say it goes down. So this is going to be our h of x. Now our main function, g of x, must be in between f and h when x is near a. So that tells us that the behavior here or here don't really matter. All we care about is the behavior as x approaches a. G of x must be in between f and h. So that means we can draw g of x so that it looks something like this. So this is going to be our g of x. So now if both the function f of x and h of x has this particular limit where when x approaches a, the y value approaches L, and if we force g of x to be in between these two functions when x is near a, then the only possible value for the limit of g of x as x approaches a must be that same value, which is L. And the reason is because it's squeezed in between them, or you can think of it as it's sandwiched in between them, hence the name squeeze theorem or sandwich theorem. Now let's take a look at why this is useful. So here we can see that we have our function g of x, and it is sandwiched in between these two functions here. So the first one is x squared, and the second one is x squared plus x minus 2 squared. And we want to find the limit as x approaches 2 for our function g of x. So let's take a look at what happens to our bottom function x squared when x approaches 2. So we have limit as x approaches 2 of x squared. So since 2 is within the domain, we can go ahead and substitute it in, and this is going to be equal to 2 squared, which is 4. Now we're going to do the same thing, but for the upper function. So the limit as x approaches 2 of our upper function, that's going to be x squared plus x minus 2 squared. Again, 2 is within the domain, so we can go ahead and substitute it in. So that's going to be 2 squared, which is 4, plus, and then 2 minus 2 squared, that's just going to be 0. So now we have the limit as x approaches 2 for our bottom function is equal to 4. And the limit as x approaches 2 for our upper function is also equal to 4. And we know that g of x is sandwiched in between them. So we can now use our squeeze theorem to say that the limit as x approaches 2 of our function g of x must be in between the limit as x approaches 2 for our bottom function and the limit as x approaches 2 for our upper function. And since we've evaluated both the lower and upper function, we get that 4 is less than or equal to the limit as x approaches 2 of our function g of x, which is less than or equal to 4. So the only number that is greater than or equal to 4, but also less than or equal to 4, is 4. So therefore, using the squeeze theorem, we have shown that the limit as x approaches 2 of g of x is equal to 4. So the squeeze theorem is helpful when we know a lower and an upper bound. This fact is highlighted in a lot of trig examples, as we know that the function sine of x and cosine of x are bounded by the values -1 and +1. So let's take a look at how we use that in this next example. We want to show that the limit as x approaches 0 of this function here is equal to 0. So note, we can't solve this algebraically, because as x approaches 0, 1 over x is approaching infinity. And we know that sine of x and cosine of x are going to be oscillating between -1 and +1. And it's going to keep doing that as x approaches infinity. So the only way for us to show this is through the squeeze theorem. So we're going to start by letting g of x be equal to this expression here. So that'll be x times sine of 1 over x plus cosine of 1 over x. Now we know that sine of 1 over x is going to be in between -1 and +1. And we also know that cosine of 1 over x is going to be in between -1 and +1. So this means sine of 1 over x plus cosine of 1 over x must be in between -2 and +2. So now we're basically almost at g of x. The only thing is we need to multiply it by x. The only issue here is that we're trying to find the limit as x approaches 0. So we could either approach from the left-hand side or we can approach from the right-hand side. But when x is negative, our inequality signs are going to flip. So therefore, we have to break this up into two parts. Part 1 is when x is greater than or equal to 0. If we do that, then what we're going to do is we're going to multiply everything here by x. And because x is greater than 0, our inequalities are not going to flip. So that means we get -2x is less than or equal to x times sine of 1 over x plus cosine of 1 over x, which is less than or equal to 2x. So now this part in the middle, that's just our g of x. So this means that if we want to take the limit as x approaches 0, and because x is greater than or equal to 0, we're approaching from the right-hand side. So this is going to be the limit as x approaches 0 from the right-hand side of -2x is less than or equal to the limit as x approaches 0 from the right-hand side of our function g of x, which is less than or equal to the limit as x approaches 0 from the right-hand side of our upper bound, which is +2x. And we can see that we can go ahead and use direct substitution here and here. So once we substitute 0 in, we get this is equal to 0. This is also equal to 0. The limit that we're interested in is sandwiched in between 0 and 0. I'm going to scroll up just a little bit. So therefore, the limit as x approaches 0 from the right-hand side of our function g of x is equal to 0. And now we're just going to do the same thing, but we're going to approach from the left-hand side. So that's for when x is less than 0. And when x is less than 0, our inequality is going to flip because we're multiplying everything through by a negative number. So we end up with -2x is greater than or equal to our function g of x, which is greater than or equal to 2x. And we do the same thing. We apply our limit, but this time we are approaching from the left-hand side. So we get this, and then limit as x approaches 0 from the left-hand side of g of x is greater than the limit as x approaches 0 from the left-hand side of +2x. And again, we can use direct substitution here and here. So then we get this is 0 is greater than or equal to the limit as x approaches 0 from the left-hand side of our function g of x, which is greater than or equal to 0. And we can see that it's sandwiched in between 0 and 0. So therefore, the limit as x approaches 0 from the left-hand side of our function g of x must also equal to 0. And now we have the left-hand side limit going to 0 and the right-hand side limit also going to 0. So finally, we can say that the overall limit as x approaches 0 of our function g of x must equal to 0. So notice how for this particular problem, we had to divide it into two cases because there was one case for when x is greater than 0 and one for when it's less than 0. This question would have been significantly easier if we were dealing with x squared instead of an x, because once you square it, we didn't have to worry about that term potentially being negative and the inequality sign flipping. Now let's do a quick recap of what we covered in this video. So we connected limits to a purely algebraic problem, and we'll see this again in the near future. We introduced our squeeze theorem, and we drew a graph to visualize how the bounds will force a limit. We also applied the squeeze theorem to polynomial and trigonometric examples using known bounds. And we highlighted how recognizing bounds and powers of x simplifies our limit problems. And now it is your turn to give this a try. can you use the squeeze theorem to evaluate this limit here? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on limits in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.